Alright, so we have a question where we have some point in space, which is the distance from this rod here. The rod has a length of L and has a total charge of Q. And the question asks, what is the electric field at this point? So in order to do this, we're going to need a few different things. We remember that the electric field given a test charge is equal to F over Q is the force. The electric field is the force on a charge for a given test charge. So this is equal to, and we remember that F is equal to F kq1 kq2 over r squared, where k is 1 over 4 pi times the permittivity. This is just a constant, so I'll just write it with k. So if I plug this in, this will give k q1 q2 over r squared over this charge. Now we're just assuming this is some test charge, so here we're just saying this is a test charge here. So one of these is test charge, so these will cancel out. So the electric field is equal to kq, whatever the charge is that we're whatever charge is exerting the electric field, causing the electric field, over r squared. So just rewrite this. K is equal to kq over r squared. Now that's just the electric field caused by one point, but we've got this long rod that is basically made up of a bunch of these points. And so in order to find the total electric field, we have to kind of sum or integrate over all of these points. So let's say we have a distance r here. So what we're going to need to do, we're going to need to integrate over this distance, which is, so r from, we're going to need to integrate from r all the way to r plus L. Alright, now what are we integrating? We're integrating the electric field caused by each of these points. So let's say if we grab one of these points, this point is an infinitely small length across this rod. It's infinitely small, and we call that dx. We call that dx. It's kind of this infinitely small length. The limit as dx goes to 0, is this infinitely small length. So how much charge is contained in this small length? Well, if we do the total charge, right? It's just a proportion. It's just a portion of this total charge in terms of the length. So, for example, if our total rod was a length of 5 and the length of our piece was 1, there would just be 1/5 of this total charge. So basically what we'll do is this. Total charge over the length gives us the unit charge, and you can also write this as lambda. This is the unit charge density. So for 1 unit of length, that's how much charge there is. And then for each unit of charge, we multiply it by whatever the length of dx is. So this is the amount of charge in one of these infinitely small lengths. And then what is the distance to the point here? It would be r plus x, whatever this distance is. So if we rewrite this, okay, the charge is q over L dx, and the distance is r plus x squared. Now, the distance here is just where x is. So for example, if x is here, then distance is r plus this section, because we're integrating from r to r plus L. So then our position will be x. Our position will be x, because that's just x is the total distance here, and it will integrate from r to r plus L, so x squared. So these guys are constants, so let's pull those out. R plus L r dx over x squared. We know how to integrate this. This is also known as x to the negative 1/2. So to integrate this, you know, what has a derivative of this? X negative 1. If you take a derivative of this, it'll just be negative x negative 2, and then this is the positive. This one's negative, so we need to make sure we add a negative in front of this. So now if we derive this, that'll be positive x minus 2. So the integration of this is this. And then we're going to compute this over r to r plus L. So to do this, we just plug in r plus L for this, minus plugging in this. So negative, let me just rewrite it here. So 1 over r plus L minus 1 minus this. And if we rewrite this, we can flip them around to look like this. And so we just put the kq over L back over here, and this is the electric field.